All right, last couple here, not too many more. Amides or amides are the least reactive. What we have seen is this lovely flow chart of ACO chlorides can go to make amides, anhydrides can go to make amides, esters can make amides, carboxylic acids can make amides. Amides can't do a lot. All right, so we're going to see a few things that they can do, but not too many. Amides can be hydrolyzed with H3O plus under acidic conditions. The products are favored at equilibrium because the NH3 group was protonated and it's not capable of acting as a nucleophile anymore, right? This is no longer a nucleophile, so we're kind of stumping that leaving group. This reaction is slow. It requires high temperatures, so we typically do not do it, but theoretically it will work. And how it works is, again, in an acid, we protonate the oxygen of the carbonyl, and then our water that is formed can be our nucleophile to attack the carbon of the carbonyl and create that tetrahedral center, right? We just created this bond right there. Now, another water is used for those subsequent proton transfers, right? This is in an acidic solution, so we got a lot of proton transfers going on. We'll transfer that to the nitrogen. Nitrogen is better at holding a positive charge, which is great. And then we will kick out our leaving group, which is the nitrogen. The NH3, the ammonia, is the thing that comes back. It is the most basic in the solution, not water. NH3 comes back so that we deactivate that nitrogen. That's the main reason why this reaction is favored, is because the nitrogen comes back to attack. Amides can also be hydrolyzed under basic conditions. Base catalyze is even slower than the acid conditions. It's the exact same mechanism as our base catalyzed hydrolysis of an ester to make a carboxylic acid. So you'll see that H3O plus workup is necessary to put the proton back on because we will make the carboxylate ion. Let's take a look at it. So hydroxide comes in and attacks the carbon of the carbonyl, and then oxygen will kick out the nitrogen. This is the equilibrium reaction, the loss of the leaving group, that's not super favored. The only reason, again, why it's favored is because of the proton transfer that occurs. This last step of a proton transfer is very, very favorable. pKa of our carboxylic acid, again, between 4 and 6. pKa of an amine is around 35 to 38, depending on what that amine was. NH3 has a pKa of 35. If we vary the R groups a little bit, then it gets a little bit higher. Now, it is that last step that renders this process irreversible. Amides are reduced by lithium aluminum hydride. The mechanism is quite different from the others that we have actually seen in this chapter. The carbonyl group is completely removed while the nitrogen remains bound to the molecule. So when we're looking at these, most often the oxygen was left as the alcohol. And notice here how that is completely removed, and we actually are going to keep the nitrogen on the molecule. So lithium aluminum hydride will make amines, not alcohols, from amides. The primary or secondary alkyl halide treated with the cyanide ion can also be used to make, or it can also be made with nitriles, or it can also be made with let's go ahead and walk through that reaction. We'll just choose a simple amide and lithium aluminum hydride. Now with lithium aluminum hydride, again, let's just write the overall reaction. And our goal is the amine. Lithium aluminum hydride needs to do one thing. It needs to actually pull off one of the nitrogen hydrogens. So we can't do this reaction with a tri-substituted nitrogen. It needs to at least be have one hydrogen on here. So lithium aluminum hydride, let's just draw that out. And that hydride reagent will pull off one of the amide protons, creating a negative charge. That negative charge has resonance, right? And that resonance is actually very, very important for us in this mechanism, because it is one of the reasons why oxygen gets removed and not nitrogen. Aluminum trihydride then coordinates with that oxygen. So we'll get an aluminum complex, again with a negative charge. This is where the second equivalent of lithium aluminum hydride will react. It's going to attack again the carbon of the carbonyl, or of the imine, I suppose we should say on this one. Awesome. And now this is where nitrogen can kick out oxygen completely. And that imine that forms can get reacted a third time with lithium aluminum hydride. So 3 versions of lithium aluminum hydride must be utilized in this reaction. First one is to deprotonate the nitrogen. Let's span back just a little bit. The second one and the third one is to add the 2 protons to our carbon. And then finally the water workup to neutralize our amine. With nitriles, remember we have the ability to create a nitrile in an SN2 reaction when either a primary or a secondary alkyl halide is treated with the cyanide ion. CN- is our good nucleophile but bad base, so it only does SN2 reactions. That lovely backside attack, kicking out our leaving group. Nitriles can also be made by dehydration of the primary amine. The reagent of choice is SOCl2. Thionyl chloride is going to be able to convert that primary amide, right? Primary meaning it has 2 hydrogens, and it needs to have those 2 hydrogens so that it can be deprotonated, so that you make a triple bond. If there are any R groups attached directly to that nitrogen besides the carbonyl, this reaction will not work. Your book does go through the mechanism, however, not as important for us. It does include a nucleophilic attack and some rearrangements. However, we're going to just know this transformation for nitriles. The nitrile actually is first can be hydrolyzed to a amide. So that reaction that we just saw is reversible with H3O plus and heat. And then it actually goes through and hydrolyzes even further to the carboxylic acid. It's very difficult for a nitrile to stop at the amide. So it's not utilized usually as a reversible reaction from nitrile formation that we just saw in the previous slide, but it does go all the way to the carboxylic acid. You can hydrolyze nitriles under basic conditions, very similar again to the one that we had seen previously. The carboxylic acid is only formed when you use that acid workup at the end of the day, because otherwise you would yield a carboxylate ion. Nitriles will also react with Grignards to form ketones. They stop at the ketone here because after the nitrile reacts with the Grignard, it forms an imine, right? And so this reaction is actually quite interesting. The nitrogen gains that lone pair and it forms an imine intermediate. So H3O plus is added to protonate that imine, and then it is also hydrolyzed in a reaction that we learned in chapter 19. Woo-hoo. The reverse of imine formation, which is then hydrolysis back to our ketone. Similar to how carboxylic acids can be converted used to alcohols using lithium aluminum hydride, nitriles can also be converted to primary amines. Again, this mechanism reacts with multiple hydride reagents and then water as that final workup step.